So here's another example of a problem where we were asked to find the absolute extrema. So here the function given is f of x equals x minus 1 to the 2/3, and the interval is the closed interval 0 to 9. So we're asked to find the absolute extrema and the location of those extrema. So let's first of all start by finding the derivative of the given function. Right, that f prime of x is equal to 2/3 x minus 1 to the negative 1/3. There is a chain rule step because we have an interior function here, but the derivative of x minus 1 is just 1, so we can take that out. So, all right, there's our derivative. Now what we want to do is ask where does the derivative equal 0 or does not exist. The reason I put this example in is that if you're not really paying close attention to the derivative, it might look like what we'd want to do is solve for f prime of x equals 0, and that would give us 2/3 x minus 1 to the negative 1/3 equals 0, which implies that x equals 1. The thing is, actually, this is not correct. The reason it's not correct is that the derivative is actually undefined at 1. If you weren't paying attention to the negative exponent, you might easily miss the fact that 2/3 x minus 1 to the negative 1/3 is actually 2 over 3 plus 1 2 over 3 x minus 1 to the 1/3, or 2 over 3 times the cube root of x minus 1. So you can see that you actually get a 0 in the denominator. So the correct understanding, although it leads to the same critical point, is that f prime of x is undefined at x equals 1 and has no values where f prime of x equals 0. So we get to the idea that x equals 1 is a critical point just the same, but it's still important to recognize why you have a critical point in any given situation. So what we have here is x equals 1 is a critical point. And just note the reason for that. So now what we're going to do is we're going to evaluate the function at its critical points and its endpoints. So the endpoints are 0 and 9, and the critical point is 1. So just recalling that f of x equals x minus 1 to the 2/3, that gives us f of 0 is equal to negative 1 to the 2/3, which is 1. F of 1 is equal to 1 minus 1 to the 2/3, which is 0. Even though the derivative is undefined at x equals 1, the original function is still defined at 1, so we can still evaluate that. And f of 9 is equal to 9 minus 1 to the 2/3. That's going to be 8 to the 2/3, which is 4. And now, of course, we just pick the highest and lowest values. We can easily see that those are here. That's the minimum, and that's the maximum. So we can say that the absolute min is equal to 0, and it occurs at x equals 1, and the absolute max is equal to 4, and it occurs at x equals 9. So there's the answer. If you're interested in what this function looks like, it's a fairly common example in a couple of different contexts in Chapter 4. What this function looks like actually is sort of like this. Let's see. There we go. So that's 0, that's 1. We'll call that 9 out there. So this is the point 9, 4. This is the point 0, 1, and this is the point 1, 0. So it does have this kind of corner here. And as you can see from looking at the graph, the conclusion we came to in part 2, that there are no points where the derivative is 0, but there is one point where the derivative is undefined, makes perfect sense. We clearly have this point here that looks like a corner, and as you can see, this function, although it gets flatter and flatter and flatter, it's never going to actually just be a horizontal line. It's always going to have a little bit of positive slope in this direction. It's always going to have a little bit of negative slope in that direction. There's never going to be a point when it's just a horizontal line with completely flat slope. And when we find that there's no point where the derivative is 0, that's what that fact is telling us. So, all right. So here's this question. Put that up.